Alright, so in this video we're going to be introducing you to Big O. Alright, so we're going to kind of motivate Big O with this idea of estimation. So over here I have a square plate, 10 by 10 meters, mass of 100 kilograms. And the question is, what's your best guess for the mass of the second square? Well, even if you didn't know the formula for calculating mass or volume or even area, you could just see that there's four of these. So for this, you can see that they're repeated 4 times in this bigger square. And so you could do just a quick estimation and say, well, I think this is probably 400 kilograms based off of that estimation, right? And that kind of makes sense if you just think about area. It's a really thin plate, so like the volume added by the thickness isn't going to impact it too much. But we know that area is like x squared, and so if you double x, then you're going to get 4x squared. And so it kind of makes sense that that would be approximately what it would be. What about volume? So volume, we have a 10 meter cube that is 100 kilograms, and the question is the one next to it. What is the mass of the second cube? Well, you can see that it's made up of about 8 cubes, and so here you can take 8 times 100 kilograms, you can get 800 kilograms. Also makes sense just based off of volume. If you take 10 and you double it, instead of having x cubed, you're going to have 2x cubed, which is the same as 8x cubed. And so that's how you kind of, approximately get the mass based off of the volume if they have the same density between the two objects. And then you can get to more complex things. So here we have something that's 3 times as tall. If we roughly estimate it using the volume on the last one, that would be like taking x cubed and then putting in 3x cubed because it's twice. This is clearly not a cube, but it's a good estimate. So we get 3 squared, and then raised to the second power, we're going to get 27x cubed. For that one. And so this is kind of motivating the idea of estimation. So we're kind of getting this idea of what happens when you take something and then you scale it up so that it's bigger. How does it affect another quantity like volume, area, etc.? So big O notation is the same. It's a rate of quantifying the rate at which some quantity grows. So we just looked at a square. As you increase the side of the length of one of the sides, how does its area grow? You could do the same thing with a circle or a cube. If you have a cube that has some length, how does its volume grow as that cubes, one of the sides of the cubes grows? So big O is the same idea, but it's a little bit less tangible because you can't see it. It's not like a physical thing that you're seeing grow, and so keep imagining that sort of like estimation of physical space as we continue to talk about big O. But we use it to measure the efficiency in our code. It's also known as computational complexity, and another way that it's often referred to is how expensive is the program as it scales, and they're all talking about the same thing. So let's look at this code here, which is an algorithm that calculates the maximum element inside of the vector. So here we have the code written. It initializes current max to the first element in the vector. Then it saves a variable n, which is the number of elements inside of the vector. Then there's a loop that goes through each element. Inside the loop, you compare the current element with the current max that you have saved. If you ever find anything that's bigger, then you reset the current max to its previous max. You've probably written this algorithm before. It's a really common algorithm that's written in an early programming class. So one thing that we could do is we could go into like the machine code or the assembly code, right? And we could just count like how many operations does each of these things take, and then we could run it again. So we could run it first with like a vector of 10, and then we could run it again with a vector of 100. And each time we could just count how many operations did it take the computer for 10, for 100, for 1,000. But we don't need to do that. We don't need to have a precisely exactly how many operations or some formula that tells you as it grows exactly how much it's growing. Instead, we want to know its order. We want to know approximately how it grows with n, where n is the size of your data. So why do we care about n? Oftentimes, our algorithms are written to be able to handle really, really large sets of data. And the algorithm isn't any good if, as the data continues to grow, the algorithm's efficiency grows, or the algorithm's complexity grows so fast that it becomes basically not useful anymore. So the way we're going to do this analysis is we're going to go through a code and we're going to define all of the operations and what they are. So we're going to go through this one time. When we do complexity analysis, we no longer will have to do this so literally, and I'll show you why in a second. So what we're going to do is we're going to think about what is a one operation. Now, whether these actually are one operations is not as important, and some of them might not actually be if you went down to assembly code, but they're approximately one. So assigning a value to a variable we're going to call one, calling a function is one, any arithmetic is one, comparing two numbers is one, or indexing to an array is one. We're going to call all of those one operations. And then we're going to count them up. So we're going to talk about each line of code, and we're going to count up how many operations there are on every single line of code. Okay? So let's first talk about best case scenario. So best case scenario would be a scenario where you have maybe a vector like this, where the max is the first element, and so you basically never have to call this again because, or you never have to call this again, I guess, because the if statement's never true. So can everyone see why that would be? So 9 is the max. Every time it compares the next ones to 9, but it never finds anything bigger, so that middle line never gets called. There's no better case than that, right? That would be the case that takes the least amount of operations. So let's do that one first. So this first line of code here is going to be 2 operations because it has a vector index, like it indexes into a vector, and it also does a variable assignment. This one does a function call, and we could also argue that there's a return from that function call, and then we have a variable assignment, so I'm going to call this one 3. All right, so what's happening on this part of the loop? Probably more than you think. So let's ignore this variable assignment, which is going to be 1, but it only happens the first time. Every other time in the loop, we're going to get a comparison, and then we're going to get a increment. An increment is arithmetic plus assignment. So all in all, with the comparison, the arithmetic, and the assignment, every time the loop runs, that's going to be 3. How about the if statement? Well, the if statement has a vector index plus a comparison, so this is 2. Then the return down here is going to have 1. Now, this whole thing happens n times, right? Because it's a loop that's going to run for n times. It's actually n minus 1 because it's not doing the first one, but we'll call it n. And so what do we get for this? If we add up all these, our loop is going to be 5n, and then we counted up 6 other things that are happening in the function. So best case, our analysis of vector max is going to be 5n plus 6. Worst case is when we have to call that if statement and it's true every time, which would be something like this. So that's going to make this line, which is a vector index and an assignment, happen every time, and that's 2 operations. So instead of having 5n, we're going to have 7n plus 6. So here we have our best case and our worst case scenario. And what we call this is O of n. So we don't care about the fact that there's that 6. It's really negligible compared to the n, and it's the same every time. So we drop that. Drop any constants. We also don't actually care whether it's 5n or 7n or 100n or 1000n. All we care is that it's n. So we call that big O of n. But what we really care about is that vector max grows linearly in proportion to n. And so this is a linear algorithm. As n increases, so for example, if you double the number of elements in V, it's 2 times more work for vector max, right? That's what it means. So that's what linear means in almost every, interpretation of that word. So let's look at another one. Let's just look at this simple function that prints out stars. So it has 2 for loops that are nested, and it just prints out a bunch of stars. So how much time will it take to run this code as a function of n using big O notation? So this middle one, we're going to say that it's just a fixed amount of work. How much cout actually is doesn't really matter. All that matters is that it's fixed and it's the same. The outer loop, as we just did with vector max, every time is going to be n. So every time you see one of those loops, if it has fixed things inside of the loop, then the whole loop is just O of n. But now we have an O of n operation inside of another loop, right? So now what we have is n squared, because we have n and n. So every time the outer loop runs, and there's an order n. Then the next time the outer loop runs, there's another n. The next time the outer loop runs, there's another n. So that becomes n squared. So the big O analysis of this is n squared. And so what does this mean? So if we have twice as large of an n, whatever n is in this case, what's going to happen to the runtime? So instead of having it double, it's going to be times 4. And this is the kind of thing that we're going to be doing. So you'll see this famous big O plot lots of times throughout the semester. It probably doesn't make too much sense right now, but it's showing you these growth rates. So we just looked at something that's O of n, and we looked at something that's O of n squared. And on this plot, you're seeing n, which is the size of the data, and then on the left is like the space or the time required in order to run an algorithm on that. So as you can see from this plot, n and n squared are very different on the plot, and they are very different, and n squared is very bad, and n and log n and n log n are much better. So that is it for our introduction to big O. We will be doing lots and lots more with it, but that's it for now. Thanks.